Consider an arbitrary set of CPU-bound processors with unequal CPU burst length submitted at the same time to a computer system. Which of the following process scheduling algorithms would minimize the average waiting time in the ready queue? A. Shortest remaining time first. B. Round robin with time quantum less than the shortest CPU burst. C. Uniform random. D. Highest priority first with priority proportional to CPU burst length. So this is a question coming from operating systems regarding process scheduling. They are saying us that a number of processes arrive to the CPU at the same time, all of which has unequal burst lengths. If that is the case, which of the algorithms given in the options will minimize the average waiting time in the ready queue? So let's consider one example of the situation given in the question. Let us say two processes P1 and P2 arrive at the same time, and P1 has a length of 3, burst length of 3, and P2 has a burst length of 5, imagine. So we will try out these algorithms one by one. Let us try shortest remaining time first. If we choose shortest remaining time first, you can see P1 has the shortest remaining time. So P1 will be chosen first and then P2 will run. Meaning P1 will have a wait time of 0 and P2 will have a wait time of whatever is the burst length of P1. So P1 has a wait time of 0 plus P2 has a wait time of 3. So the average is by 2 equals 1.5. Now let us try longest remaining time first. Now this longest remaining time first is whatever is given in D. It's saying highest priority first with priority proportional to CPU burst length. Meaning the process having the longest burst length will have the highest priority and that process will run first. So it is same as longest remaining time first algorithm. If we choose the longest remaining time first algorithm, P2 has the longest remaining time. So P2 will run first and then P1 will run first. Meaning P2 will wait for 0 time and P1 will wait for the length of P2, that is 5. So the average waiting time would be 5 plus 0 by 2, that is 2.5. Now let us consider round robin algorithm with time quantum equal to 1. That was given in option B. Round robin with time quantum less than the shortest CPU burst. Here the shortest CPU burst is 3. I have chosen a time quantum of 1 which is less than 3. So if that's the case, for the first time quantum P1 will run. After that P2 will run, after that P1 will run, after that P2 will run, after that P1 will run. Now P1 has used up 3 time quantum, meaning P1 will be over now, meaning P2 can run freely after this. So P2 will run from, so when P1 is over the time was 5, so from 5 to 8 P2 will run freely. Now let's try to calculate the wait time here. P1 started here and P1 was ending here. In between there were 2 cycles in which P2 was running. So these 2 cycles are the wait time of P1. So P1's wait time is 2. Similarly, if you look at P2, P2 came here. So P2 started from here only, that was the arrival time, and P2 is finishing here. In between, for 3 cycles of P1, P2 was waiting. So wait time of P2 is 3. So the average wait time is 2 plus 3 by 2, that's equal to 2.5. So if you take a look at all these 3 algorithms, you will see that the one minimizing the average wait time is shortest remaining time first algorithm. So among options A, B and D, A minimizes the average wait time. Now option C is uniform random. Uniform random means it can take a random, it can run the process in a random order. So uniform random can become shortest remaining time first or longest remaining time first or round robin. It won't become round robin because round robin is having time quantum, right? So it won't be round robin. Uniform random can be shortest remaining time first or the longest remaining time first. So it can't guarantee the smallest average wait time. If it becomes longest remaining time first, then it will have a higher wait time. So uniform random is also not correct. So here the answer is shortest remaining time first. That's the one which minimizes the average wait time.